Hi everyone, my name is Zhao Jia. I'm from Simon Fraser University. I will talk about our work, microphone array backscatter and application-driven design for lightweight spatial sound recording over the air. This is a joint work with Gong Wei and Professor Liu Jiangchuan. Advanced acoustic sensing technology plays an important role in a wide range of consumer and industrial IoT applications. It records spatial sound and processes them to get rich information. With this technology, we can do a lot of things such as sound source localization, noise reduction, acoustic diagnosis imaging, and machine condition monitoring. When recording spatial sound, we usually use a microphone array to simultaneously record multi-track audio signals so as to reconstruct the sound field in a space. These microphone array devices are specialized with large size and power-consuming hardware. So we think about a question, in practice, can we provide such high-dimension acoustic experience in a more efficient way? Here we mean if we can have a low power and lightweight phase array microphone to wirelessly record spatial sound. If so, it can be used for small-scale sensing devices. Such a design may change a complex 3D spatial audio recording system into a simple consumer wearables working anytime and anywhere. Let's first look at what a regular microphone array solution looks like. Microphone array works by recording the time domain waveforms of each audio track and calculate the difference between each other. The first challenge posted on a lightweight design is that it must do precise multi-track synchronization with digital components. They rely on embedded synchronization algorithms or even a dedicated single board computer to run a multi-track audio processing software. It is also challenging to transmit a big amount of data that comes from multiple microphone array elements. Our key idea is an application-driven design that transforms the microphone array synchronization function entirely from a digital domain into a lightweight analog domain. It is a time multiplexing that can reduce data amount. We can also combine it with a backscatter design for low streaming latency and low power. Our design starts from a very simple principle. Let's use pulse position modulation to sample and recover an analog signal. We can see that in the pulse position modulation, the analog information is encoded by a relative position of a narrow pulse compared to the start position of each triangle waving sampling. And the decoding can simply use a low-pass filter. We want to use pulse position modulation for audio encoding, but things becomes complex for microphone array design. This figure shows how we do multiplexing and synchronization together using pulse position modulation. And an analog multiplexer ensures to access all the audio tracks. During each period of triangle wave sampling, the comparator outputs a pulse width that represent instant analog information. And we use a monostable multivibrator to generate the pulse position as the encoded analog data. For multi-track audio synchronization, we use a truth table to control the multiplexer to do the row polling of multiple tracks. And the sampling period is controlled by a synchronization clock signal. We can also eliminate the synchronization clock if we use pulse interval to represent the analog information. This is a differential pulse position modulation. At the reader side, it does not need a synchronization signal to recover the original analog data. For each track, we use two different monostable multivibrators. The output of a monostable multivibrator can generate a narrow pulse given a negative edge. The output monostable multivibrator marks the end position of a sampling duration. The sampling monostable multivibrator can generate a trigger pulse of a fixed race. So far, we have encoded the multi-track audio signals as pulse position baseband signal. Our next question is how to transmit such a baseband. Traditional sensor communication uses an RF transceiver, which is power hungry because it needs high frequency oscillators to generate a carrier. Unlike the traditional way, backscatter communication uses reflected signal to transmit data. In the backscatter system, the information is conveyed by changing its antenna's impedance. This motivates us to use backscatter for our baseband transmission. It raises another question as to whether backscatter communication can support high-performance multimedia sensing applications. We know that multimedia sensing usually takes much more better ways than the scalar data sensing. As shown in the table, uncompressed multi-track audio bitrate can be of multiple megabit per second. So it is challenging to use backscatter without adding extra digital processing components. Previous studies have shown that analog backscatter is suitable to transmit multimedia data compared to the digital backscatter. So our goal is to adapt our PPM baseband to an analog backscatter system. We use pulse position baseband signal to modulate a square wave. In this way, the analog data is encoded as the time variant phase of the square wave, and two consecutive pulse position intervals have 108 degrees phase offset. Since the excitation is usually located in the uplink coverage between backscatter and reader, the excitation signal can impact the decoding. Our phase modulation to the pulse position baseband can generate a 10 megahertz frequency offset between excitation and the backscatter signal. In this way, the self-interference is canceled. On the side of the receiver, the demodulation includes 3 steps. The first is to downconvert by removing the excitation carrier. Then we use a conjecture phase discrimination to demodulate the pulse position baseband from the phase modulated signal. The last step is to use a low power filter to recover each audio track's waveform. We built a microphone array backscatter sensor prototype using PGA discrete components and off-the-shelf IC devices. We only use this prototype to test the functions we design. We can implement the monostable multivibrator in 2 ways. The first one uses two resistors, a capacitor, and a NAND gate. It can generate a narrow pulse immediately after a negative edge. Another implementation uses an inverter and RC differential circuit and a diode. It utilizes the charging phase of an RC circuit to generate a positive edge or as the pulse position. We also implement the row polling logic and phase modulation in FPGA to generate control signals for 3-input 8-channel multiplexer we get the output of 2 toggle flip-flops with inverse edge trigger and use them as 2 control signals for the multiplexer. Then we build a circuit with XOR gates and positive edge toggle flip-flop to convert 2 control signals into the third one. The phase modulation circuit converts a pulse position baseband to a phase variant square wave. We use a positive edge toggle flip-flop to mark each pulse position. We use power monitor to measure PCB power consumption, and we use a Cadence IC design platform to do power simulation. For 8-track microphone array, our design can consume as low as 175.2 microwatts of power using IC design simulation. We first evaluate the streaming latency of using different microphone array solutions. We compared our design with a regular solution that use sound cards, spatial sound processing tools, and wireless adapter. The regular solution has a millisecond level latencies, and our solution largely improves the performance by making microsecond level streaming latency. To examine the fidelity of the demodulated multi-track audio signals, we calculate the Pearson correlation coefficient. It compares the similarity between the original sound waveforms and the envelope of the demodulated sound waveform. For a sampling rate larger than 30 kilohertz, we achieve a correlation coefficient larger than 0.7 within a distance of 7 meters. In the line of sight experiment, the communication range is up to 28 meters, and given the sample rate of 50 kilohertz, the signal to noise ratio decreased from 45 dB to less than 15 dB. The non-line of sight experiment shows an SNR over 35 dB and a distance of 1 meter, and it decreased to less than 15 dB when the sensor to radar distance increased to 6 meters. We also show that the backscatter signal quality decreased quickly as excitation to sensor distance increases to 3 meters. We use our microphone array backscatter sensor to build an acoustic imaging system that can visualize sound source location. The distribution of location error shows that about 66% of trails falls within an error range of 2 centimeters. We also design a beamform filter system for noise reduction using our phase array microphone. Our result shows that the system can improve audio signal quality by up to 15 dB as compared to a single track microphone. In the future work, we will focus on some limitations of our current implementation. First, we want to extend the type of excitation to a wide range of RF signals from commodity radios. Second, we need an energy harvester for both sound and RF signals. And we evaluate how it can support a battery-free design. We may also use encryption and strict access control in our future design to address the security issue. That's the end of my presentation. Thank you for listening.